We're going to talk about some basic ideas of probability. We're going to come back to this again and again. The phrase is think like a statistician. We're often going to be talking about hypothesis testing, and we want to set up what we call a null hypothesis, which asks the sort of oddball question, how likely is it that I'm being fooled? Not how likely is it that I'm right, but how likely is it that I'm wrong? That is, what if there were actually no relationship there? Yet a person could be fooled into thinking there might actually be some pattern or relationship there. And I understand it's a little bit backwards. You're not trying to prove that you're right, but you're asking, how would you know you were wrong? In the statistical testing apparatus, we distinguish the null hypothesis, which we often notate as H0, from the alternative hypothesis, HA. We want to set rules how to distinguish if we're being fooled. We want to set out those rules even before we do the testing. In order to set up those rules, we have to have a good understanding of what actual randomness looks like. So let's start by thinking about randomness in a case of games. We all have the experience, if you watch any kind of game, you know sometimes the better team or the better player loses. It's inherent randomness in the event. Frankly, otherwise it's not very interesting. Now, randomness is kind of the point of why people play the game. If there were no uncertainty about the outcome, then not much fun to watch. So, all right, let's get a little formal and say a team has a probability P of winning, and so 1 minus P probability of losing. Keep it simple, we're going to assume for now there's no ties. We come back afterwards and make it more complicated, but that's enough to start. If that team played 2 games, then we'd have the set of outcomes shown in the table there. The team could win game 1, those are the columns, and then the team could win game 2, those are the rows. The first outcome at the top left is if they win both games. Bottom right corner is if they lose both games. The off diagonals are where they win one and lose one. Either they win the first and lose the second, or lose the first and win the second. Now, one bit of subtlety here is when we're writing out these probabilities, we're assuming these are unrelated outcomes. There's no such thing as streaks, or more precisely, there's no such thing as influence from streaks. A team might win 2 games in a row, but that doesn't necessarily mean they're more likely to win the next game. We can later test this hypothesis, look at the question, to what extent is that true in different sporting events? Sometimes called a hot hand in basketball games, people talk about that. Somebody sinks a bunch of shots. Are they more or less likely to keep on sinking baskets? Answer, it's complicated. But anyway, having made that simplifying assumption, we write out the notation. What's the likelihood of, or probability of 2 events, A and B, which we denote with that little upside down U sign, that's the intersection. What's the likelihood of A and B happening? As I was saying earlier, if A and B are independent, then one consequence is the likelihood of A and B happening is just the unconditional probability of A happening times the unconditional probability of B happening. In this case, the probability of winning game 1 is P, probability of winning game 2 is P, then the probability of winning 2 games in a row is P times P, P squared. If the teams are evenly matched, where each has a 1/2 probability of winning, then the likelihood of winning 2 games in a row is 1/2 times 1/2, which is 1/4. The likelihood of losing 2 games in a row is symmetric, 1 minus P times 1 minus P. Again, if P is 1/2, then again, that's 1/4. Then the off-diagonal terms are each P times 1 minus P. If P is 1/2, then the box is, again, probability of 1/4. Now, what if we go to 3 games in a row? We did 2 games in a row, let's do 3. The notation we were doing on the previous slide gets a little bit cumbersome because a 3-dimensional table is kind of rough to visualize on a 2-dimensional screen. So instead, we're going to write it out longwise. Win 3 games in a row, what's the likelihood of winning 3 in a row? There's P, probability of winning the first time, times P, probability of winning the second time, times the P, probability of winning the third time, P cubed. What's probability of win-win-loss? That's P times 1 minus P. With our assumptions that the team don't get better or worse over the series, a loss in any of the 3 games would still end up with 2 wins and 1 loss. So what's the likelihood the team wins the series, i.e. 2 out of 3 of those games? Just add up the probabilities in each of those 4 left-hand boxes. Add them up. Probability of winning the series is p cubed plus 3, because there are 3 possible ways of getting p squared times 1 minus p. What's the probability of the team losing the series? What's the probability of that happening? Again, we just add them up. What about 4 games or 5 games or 6 games or more? Well, as you start to do the algebra, trust me, it's great fun, really exciting, you'd start to see the coefficients forming into what you might remember as Pascal's triangle. Hopefully you remember that from algebra class. If I scale those coefficients by the total, then those will become the coefficients of the normal curve, which is actually the way that mathematicians figured out that draws from a binomial distribution are going to converge to a normal distribution, because they figured out those coefficients, worked them all out, figured formulas for how to represent those coefficients in Pascal's triangle. Kind of cool.